Good evening, everyone. Welcome to the week 5 live interaction session. Before we begin our session for today, let's just wait for a few minutes for others to join. So let's begin our session. Let me just present my screen. I hope my presentation is visible and I'm audible. Okay. So, welcome everyone to the week 5 live interaction session for the course Polymers Concept, Properties, Uses and Sustainability. This course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. Myself Pratyumnan, a research scholar from the Department of Chemical Engineering. I conduct live interaction sessions for this course, and we have so far come across 4 live interaction sessions, and we have looked out on the properties of the polymers. Specifically, we have dealt a lot on the concepts of the polymers. So the very first week live interaction session was on a brief overview of the properties, concepts, uses and their sustainability. Whereas from week 2 onwards, we mainly focused on the different types of concepts, and today for the week 5 live interaction session we will be looking on the properties of the polymers. Previously also we have discussed about few of these properties. So today we will keep continuing with the chemical and the mechanical properties of the polymers. So in the last live interaction session, we discussed more on the glass transition temperature, and um, does uh, how does a polymer behave at temperatures below Tg and at temperatures above Tg. We discussed on that. We discussed on the relaxation process and the concept of free volume, and how does Tg and the free volume are interrelated both qualitatively as well as quantitatively. We have seen the kind of uh, relation between the free volume as well as the glass transition temperature. Apart from this, we have also discussed in detail in the on the relaxation process about what happens if the relaxation process is fast and what is the significance if the relaxation process is slow. Then we have discussed about what happens if the temperature increases, decreases, its effect on the free volume as well as relaxation process. We have discussed these things in detail. Apart from that, we have also discussed on copolymers and the types of copolymers. What are the different types of copolymers, like alternating copolymer, then if monomers form a homopolymer, and if two homopolymers are covalently linked to each other, what it is called. And we have discussed about the reactivity ratios. So if you have two monomers, what is the probability that if I combine these two monomers, it will result in the formation of an alternating copolymer, or what is the probability that I will be getting a random copolymer or a block copolymer by mixing these two monomers. So we have discussed about the reactivity ratio and the preference, and how to decide if whether combining two monomers gives you a polymer of your need. So apart from that, we have discussed about the calculation of the Tg values for both, for the copolymers and for the blends as well. So this week we will discuss more on the mechanical properties of the polymer. So we will initially start discussion on the mechanical properties, then we will move towards the composite formulation from the polymers, like why it is required to form composites out of polymers, or what are the advantages of composite formulation for our everyday use. So this mechanical response or mechanical properties of a polymer, initially speaking, we speak about the uniaxial tensile. So there are different types of you can say there are different types of loading. So one of them is the tensile, and in that the most simplest one is the uniaxial. So can anyone tell me what exactly this word uniaxial means? Anyone? Uniaxial tensile, or we have uniaxial tensile, biaxial. So what is actually meant by this uniaxial? So uniaxial, what it actually means is something that the loading or whatever you're doing is relevant only to one particular axis. So if I say uniaxial tensile, that means I'm going to stretch or I'm going to apply a tensile load only in one particular direction. So if it, suppose I say it's a biaxial, then the force of the load is applied on the material in two different axes. So this is the typical difference between a uniaxial or a biaxial. So uni means one, bi means two. So majorly all these kind of loading actually happens at a constant rate. So at a constant strain rate. So this strain rate is something that is very important in case of that of the polymers. May or may not be in case of other engineering materials, but when polymer is under discussion, the concept of strain rate is very important. The major reason is basically because of the viscoelastic nature of the polymer. So since a polymer exhibit both the viscous behavior as well as that of the elastic behavior, the rate of strain at which you the rate of strain or the rate at which you vary the strain have a significant influence over the polymer behavior when it is subjected to some sort of loading condition. So depending upon the type of polymer, the mechanical response could be different. So let's say I take a polymer sample, or let's say a block of polymer sample, and then I subject it to uniaxial tensile. So depending upon the type of polymer and the properties of the polymer, the response will be different. So for example, we can have totally three different type of responses, and you can actually classify the polymers based on the type of responses as brittle polymers, ductile polymers, and flexible polymers. So brittle, as such the word suggests, when you as such the word suggests, it cannot handle much of the stress within the material. So brittleness, as such, it means that it cannot stretch, it cannot undergo more deformation compared to the other materials. That is the reason it is brittle, because once you stretch it to a certain extent, what happens is these polymers actually break. So the semicrystalline polymers specifically exhibit this brittle nature. So the main reason for the brittleness lies in its microstructure, or lies in its structure, you can say. The reason is that these polymers typically have a more ordered close packing. So since these polymers are semi-crystalline in nature, they have more ordered close packed structure and stronger forces of attraction that are holding them together. So because of this, what happens is that the conformational disorder that is present in the system is a lot less. So because of the ordered nature of the crystal system and then the stronger forces of attraction, these polymers cannot undergo deformation even if we keep increasing the stress. So that is the reason these brittle polymers crack when it is stretched or deformed. So when you take a brittle polymer and then, or semi-crystalline polymers, and then if you stretch it, what happens is after a certain amount of loading, you first thing is you won't be able to stretch it to a greater extent, but as you keep increasing the stress or the loading on the sample, after a particular point the sample will crack. So this is something which we typically observe in case of polymer films. So uh, what we try to do is we try to make a polymer film through different coating techniques, or through different uh, film forming techniques, and then we take these polymer films and then try to stretch it. So if the polymer film what we have is brittle, then the deformation will be very less, and then you can see that they start to exhibit the cracks can be seen within the polymer film. So this is about polymer film. But if you come to, let's say, a ductile polymer, then in that case what happens is that the forces of attraction is not as strong as what you have observed in the cases of brittle materials. Here the force of attractions are quite weaker in nature. So the amount of stress that will be required to deform the material, or if you deform the material, the deformation will happen, but this will happen at a much lesser, or this will happen at less stress. Like if you use lesser amount of stress, that would be enough for the polymer to stretch. So this is about the ductile polymer. Whereas in case of the flexible polymer, they are more like rubber and thermoplastic elastomers. What happens is they can accommodate very large deformation. So if you stretch them, they can even, at a very small amount of loading or the stress, they can even stretch up to 800 to, even there are reports of 1000 percentage of increase in the length of the polymers. So they are more of rubber like material which has a highly cross linked structure. And then the major reason why they are able to deform to such a greater extent is basically because of the order higher conformational disorder present in their structure. Since these polymers are mainly entangled in nature, they have a higher conformational disorder. And because of this, what happens is if you stretch these polymers within a very small amount of strain, within a very small amount of stress, they are able to accommodate a larger amount of strain, and they can even be stretched up to 800, or even there are, as I said, even there are reports of 1000 or 1200 percentage of its original length. So this is more of the flexible polymers, or basically the rubber like materials. So if you compare the modulus of these three classes of polymers, as we discussed, one is brittle, ductile and rubber like, then you can observe that, just a second, let me write it. So what you can observe is that in case of bulk modulus, in case of modulus, so the modulus of brittle polymers will be much greater compared to ductile polymers, which will be greater compared to flexible elastomers. So I mean, as we discussed now, could you explain this trend? Why such a trend is exhibited in this case of polymer systems, or in this uh, polymers? Like, why is such a mechanical response we can see in these polymers? Brittle polymer has higher modulus compared to your ductile, and then the elastomers. You can quantitatively tell this based on, I mean, if you have the graph with you right now, then you can also use the graph to explain these. But if you do not have the graph, then you can also quantitatively explain why the modulus is in this particular order. Using graph also we can say. Any idea why? So if you see in case of brittle polymer, as I previously also discussed, what happens is even if you increase the amount of stress to a very larger extent, the strain that is developed in the material is very less. So if you say modulus, let's say that by Hookean law, modulus can be defined as a ratio of stress versus strain. So if you use this, I mean this everybody must have an idea of the Hookean law. So where you actually consider your material as an energy spring, and based on that you can describe this equation. You can write this equation. So if you see for a brittle polymer, stress will be very high, but at the same time for that high amount of stress, the strain developed in the material will be very small. So it is basically because of that. So stress is high, strain is small, so the modulus will be high. But for the ductile polymer, strain will be quite large, at the same time stress will be reduced. So that is the reason it has a lesser modulus compared to the brittle or the semi-crystalline polymer. But if you take for elastomers, for a very small amount of stress is sufficient to stretch the polymer to a greater extent. So the strain that is created in the material will be very large, but then the stress that is required to develop this strain in the material will be very small. So because of this, the modulus in case of the flexible elastomers will be very less. So that is the reason why if you take these three systems into consideration, and then if you try to kind of compare them based on their modulus, then the brittle polymer will have a very higher modulus compared to your flexible elastomers and then the ductile polymers. So this is typically the reason of why this is the trend for this brittle, ductile and flexible elastomers based on their modulus. So in case of semi-crystalline materials, as we have previously also discussed or seen, that polymers cannot be crystallized, like completely crystallized. 100% crystallization is not possible in case of the polymer systems. So no matter what polymer that you take or crystalline polymer that you take, it will be semi-crystalline in nature, which will have both the crystalline domains as well as that of the amorphous domain within the structure. So a modulus of a semi-crystalline polymers is usually a function of crystalline regions, or you can say crystalline domains, and amorphous domains. So this is typically this, the very similar to the examples that we have seen in the last two classes, where we wrote density or the specific volume or your glass transition temperature for a semi-crystalline system as the additive of the particular physical property for the crystalline region as well as that of the amorphous region. So you need to take under the consideration of both the crystalline and the amorphous region when you calculate the modulus of the semi-crystalline systems. So each of these domains will have their own elastic modulus. So can anyone tell me which will have more elastic modulus? Is it the crystalline one or the amorphous one? So let's consider a semi-crystalline polymer, and let's say it has a crystalline region, A as a crystalline domain and B as an amorphous domain. So you need to have both of these modulus of the crystalline and the amorphous domain to calculate the modulus of the semi-crystalline polymer that we are taking under consideration. Now my question is, which one of them will have higher modulus? Whether will the crystalline region have a higher modulus, or will the amorphous region have a higher modulus? You can actually think of this basically based on the order of packing, or order of packing of the polymer chains within these two regions. How is the packing in case of crystalline region and amorphous region? It's something very similar to what we saw in case of density of crystalline versus amorphous region. So we told that the density of the what do you say, the crystalline regions or the crystalline domain is greater compared to the density of the amorphous domain. The major reason is basically because for a unit volume of element under consideration in both these regions, the mass of the polymer in case of the crystalline domain will be greater compared to that of the amorphous domain, because the number of polymers will be closely packed in case of the crystalline region, so its density will be greater compared to the density of the amorphous region. Similarly, use that concept to explain which can have the higher modulus. So that I think it will not be of much difficult, but I'm leaving it to you guys to go through to basically evaluate which region will have a higher modulus. So as when we discuss about the mechanical responses of a polymer or the mechanical aspects of a polymer, we are also we also need to be interested in defining few of the terms, a few of the mechanical um, in a mechanical terms for characterizing these polymers or the mechanical properties of the polymers. So the first one is nothing but it is the ultimate tensile strength, and then the second one is the toughness of the polymer. So any idea on what are these two quantities called? Anyone? I mean, what these are the two parameters which we use to characterize the mechanical properties of the polymers. But what do these two terms represent, or what do they signify? These two are the mechanical properties. You can say these two terms are something which many of us may be very familiar, because these are something this which we are learning uh, you know in physics as well as in engineering classes. So these two aspects of mechanical or for access for aspects for analyzing the properties of the material should be like everyone should be well aware. So I think everybody must be very well aware of what does the ultimate tensile strength actually means. So it is nothing but how much load a material can take, a material can take before it fails or breaks. So you keep on increasing the amount of load in the material, and then for the amount of load there will be proportionally a strain which will be developed in the material. Let's assume that the stress and the strain are linearly proportional to each other. So as you keep increasing the stress, the strain will also keep increasing. But there will be a point beyond which if you increase the stress, the strain, the increase in the strain will be not linear, but it will be more, you can say it will be more vigorous. So the deformation will be large after a particular point of time or after a particular point of stress. So that stress is basically called as your ultimate tensile strength. So how much load a material can take before it fails or breaks is called as the ultimate tensile strength. There is another one aspect which we need to look upon is nothing but is the toughness. Toughness is nothing but the amount of energy that the material can observe and absorb before it fails. So that is basically at what load your material breaks. That is ultimate tensile strength. Here is nothing but the amount of energy that the material will absorb before it fails. So you can also call this as energy per unit volume. Or if you see from the stress versus strain curve, then you can actually comment this as area under the stress strain curve. So this is the ultimate tensile strength of the polymer, ultimate tensile strength and the toughness. So can anyone tell me now, based on these two quantities, whether the brittle polymer will be more tough or less tough, or you can say soft. So I want people to comment about this brittle, ductile and flexible elastomer based on their ultimate tensile strength and toughness. How will the how will these things vary, or what you can actually comment about these three systems of polymer? So the thing is whether your brittle polymer will be tough or will it be not, or it's not going to be tough. Similarly, which of the three, so we have actually divided the polymer system based on their modulus, or you can say their mechanical response as brittle, ductile and flexible elastomers. So based on this, based on the ultimate, so which of them will have high ultimate tensile strength and which one will have a lower value of the ultimate tensile strength? I think ultimate tensile strength will be a bit simpler, because again it's basically the load at which your material is going to break. So brittle polymers can actually accept a far more load or far more stress compared to your flexible elastomers and the ductile polymers. But what about toughness? Which will be more tough? Well, is it your brittle semicrystalline polymer or is it your flexible elastomer? You can actually think this from the perspective of area under the stress strain curve. Toughness. So it is basically, let's leave about the concept or the definition of toughness. Let's see only that from the area under the stress strain curve. So if you think that from the perspective of a stress strain curve for a flexible elastomer, you can say that the flexible elastomers are more tough compared to brittle brittle semi-crystalline polymers. Is it right? This is because they actually absorb far more energy into the system when you actually apply the loading. So what happens is when a loading is applied, almost all of its internal, what happens as such is that when you apply tensile loading or any sort of loading, or when you subject the material to loading, the internal energy of the material is going to get converted and is going to be conserved, or is going to be conserved into the material polymers as strain energy. So the amount of energy that the toughness as such, we say it as the amount of energy that the material can absorb before it breaks. So if you see for a flexible elastomer, since it can stretch up to greater so the flexible elastomer can stretch greater than to an extent much greater than its original dimension. Thus it basically absorb more amount of energy, so it has a greater toughness compared to your brittle polymers. So this is about the toughness and the ultimate tensile strength. So ultimate tensile strength, the amount of load that a material can bear before it breaks. Toughness, the amount of energy that the material can absorb before it breaks. So based on that, we can again classify them, or we can actually compare all the three classes, all the three types of polymers, and we have done that. So tensile loading, as I said, is not just the only way to subject the material to some sort of mechanical or loading conditions. Apart from tensile testing, there are also multiple other ways of testing a particular material, or basically you can say that there are also other different ways to understand about the mechanical properties of the polymer. So apart from the tensile loading, there is also something called compressive. So compressive loading or compressive strength. So here what happens is the material is compressed, and then depending upon the amount of load that the material can compress it to, we can calculate its compressive strength. Then we have flexural strength. So this basically determine how much bending is possible in a material. How much a material can bend is usually given by this flexural strength, or you can say flexural loading. If you say flexural loading, then then it actually means is that we are going to bend the material under loading conditions, more related to bending or bending. Then you have shear. I hope everyone will know. It's just that shear, I hope everybody knows this. Then next is the torsion. So torsion is nothing but, here what you do is you basically twist the material, and then based on its ability to twist, you actually calculate the torsion strength of that particular material. Apart from these kind of terms, we are also supposed to look at some apart from these mechanical terms that we are seeing right now, we are also supposed to have an idea of few other terminologies, such as the stretch ratio. So since these flexible elastomers, as I said, it can stretch up to greater extents, and we also have literature evidences where the stretching can be, where they have observed stretching of polymers of up to 1,000 times of its original dimension. So this particular terminology is of a greater concern when we use elastomeric materials. So stretch ratio is nothing but it is defined as length of the deformation length, you can say deformation length to the undeformed length or the original length of the material before it is subjected to any kind of loading. So this stretch ratio terminology basically is used to represent how much a material can stretch from its original length. So this is typically represented as 1 plus E, and it is stated that the value can go the value of the stretch ratio can go from or can be between or is in the range between 1 to 8. Again, there are so this typically means that you can stretch the material to 8 times of its original length. Instead of saying expressing it in terms of percentage like 800% or 900%, it's an alternative way to say that you can stretch your material 9 times or 8 times greater than or 8 times of its original length. So apart from that, we also have concepts of linear elasticity and non-linear elasticity. So this linear elasticity is a term wherein you can use this Hookean law as we have described previously, and then explain how stress and strain are proportional to each other. And there is also another one concept of non-linear viscoelasticity, or sorry, non-linear elasticity. So this concept of nonlinear elasticity comes into a picture when there are large deformations are possible in the material for a small amount of stress. Large amount of deformations are possible in the material for small amount of stress. So this is something typically what you actually see in flexible elastomers. That is, they have that is when you stretch these material, they exhibit a larger deformation. And this is, as I said, typically because of the higher conformational disorder that these systems have, and then so because of which the polymer chain have enhanced the segmental mobility. And yeah, so this is the reason why there is a larger deformations are possible, and in this case you cannot use the linear elasticity concept, so we actually go for a non-linear elasticity concept, where we describe or where we express the stress as a function of strain, but using different models such as your neo-Hookean model. And so after this, we have to discuss something about the composite formulation. So we do study about a lot about these mechanical properties of the polymers, and the typical reason why we do so is to basically to understand or to I mean the understanding of the mechanical properties of the polymer will help us to understand what kind of polymer systems or how to test a polymer systems, or basically what are the properties, mechanical properties that we can analyze from, or that we get from these polymers, so that it can be applied in a particular application. So as such, if you see the polymers, even though some of the brittle polymers are have a very high ultimate tensile strength, or have a very high modulus, but these are not comparable to that of metals or ceramics. So they are high compared to flexible elastomers. The brittle polymers exhibit higher modulus, but that is again less compared to your metals or the ceramics or other engineering classes of materials in general. So typically, to improve upon the properties of the polymers and then to basically use them in particular application, we try to, I mean, even though we can do major modifications, but still we cannot attain the mechanical properties similar to that of the other engineering classes of material, but again we can improve upon the properties of the polymer. So in order to do this, or in order to improve upon these properties of the polymer, we basically go for composite formulation, so that we can improve upon the certain properties of the polymer based on our interest to an extent greater, or to an extent greater compared to the pristine polymers that we have in our hand, or that we have with us. So in case of composite formulation, there are totally two different phases, or you can say two different components. One is basically called as the matrix, and then the other one is called as the reinforcement or the filler. So the matrix is a continuous phase, whereas the filler or the reinforcement that you add to this matrix is a discontinuous phase. So composite is typically made up of two, where polymer is so in case of polymer composite, the polymer is a major component which forms a matrix, and then the second component is called as the reinforcement or the fillers. Different types of fillers can be added. So any idea on what kind of fillers are typically used in composite formulation, irrespective of what applications are they are intended for? Any idea? So composites are typically framed or constructed, or you can say designed for various functionalities. So I am just asking for few examples, irrespective of their irrespective of what they are intended for whichever, for whatever application they are intended for. Examples of fillers. Yes, anyone? I think there might be anyone would know that what kind of fillers can be used for this composite formulations. So you can look up in the internet, because the amount of fillers are numerous. So many fillers can be used in case of these polymers, or in case of for formulation of polymer composite. So and each of them has a specific function for, or a specific reason for them being added into this polymer matrix. So you guys can always have a look at it. If you just type in composite formulations or composite materials or polymer composite material, you will get a list of polymer composite, their fillers, matrix, and what applications they are typically used for. So as I said, the composite formulation is primarily to tailor the properties of the polymer materials so that it meets the human demand or human needs. So when you add two different materials, or when you add one material to another material, obviously it is obviously they are actually going to interact with each other. There would be interactions, right? Because when you are having a matrix, and then when you are going to add fillers into them, there is going to be interactions, which is quite obvious. So the type of interactions that actually exist between these two um, systems, or between these two components, actually govern the properties of your composite. You can also put it in this way, that the interplay between them is very important, which affects the properties of the final composite that we get. And based on this understanding, the reason why this understanding is important is because with this we will be able to tailor the materials that we require, or tailor the properties of the polymer composite that we want for our needs. So what kind of nanofillers I can add, or basically if I add let's say for example a nanoparticle. So nanoparticles can also be used as fillers. If I add a nanoparticle to my system, will it give good or a better mechanical properties compared to if I use fibers? Or if I use fibers, will it give better mechanical or better electrical properties compared to what I get if I use nanofillers in place of fibers? So this is something, since the filler number of fillers are numerous in number, so we should be careful enough to choose what filler is required for our application, or what type of filler is required, or what dimensions. So that is also an important consideration, whether we need long fibers or short fibers for our application, and the interplay between them is also important. So if I'm going to add a filler to, or a reinforcement to my matrix, will they be will they be able to interact with each other favorably, or will there be some sort of a phase separation between both this reinforcement and the matrix, and the properties of the material, or the final polymer composite will be weak compared to the individual properties of the filler and the reinforcement. So it can also happen in this way. So if we do not choose our fillers and the matrix properly, composite formulation should be done very carefully, because our goal at the end is to improve upon the properties of the system. But if we choose wrong fillers, or if we do not know what type of fillers to use, or as I said, if we choose wrong fillers, or if we do not know about the quantity of the fillers that we need to add, or if we do not have an idea of whether they will interact favorably with each other, then the property of what we intend for in the polymer composite will be weak, or will be less compared to the same property in their individual components. So let me write this. If nanofiller, or let's say instead of writing nanofillers, if reinforcement are not chosen wisely, then the property of the polymer composite formulated will be poor or weaker compared to the, I'll just write it as a sentence, so will be poor or weaker compared to the properties of their individual, you can say, constituents. So this is also very much possible where you get a material with the deteriorated properties. So that is the reason the design and the selection of the reinforcement, the selection of the reinforcement matrix and the design of the polymer composite is very critical and crucial. So when I talked here about the properties, what are the properties that we typically want to improve? So there are few properties which we typically want to improve, and I mean to say, these are the properties um, which are commonly discussed. First one is your mechanical properties, then you have electrical properties. Again, majority of the polymers that you see, they are flexible, but they may not be as suitable for load bearing application. So you need to actually add reinforcement fibers to them so that their property can be enhanced. And in case of electrical properties, if you see, majority of the polymers are insulating. Conducting polymers are also insulating or semiconducting in nature. So in order to improve upon the electrical properties of the polymer or of the conducting polymers, we tend to add nanofillers to the system so that their electrical properties can be enhanced. Apart from that, even thermal properties can also be enhanced by adding nanofillers to the system, or I can say, instead of saying nanofillers, some sort of a reinforcement to the system. And even barrier properties can also be enhanced by using a filler or a reinforcement. So the typical example that is actually discussed in the course or in our in the course is wood. So wood is a natural composite. It's a natural composite which is made of actin and lignin. So here, which one is the continuous phase and which one is the discontinuous phase? Or to be more direct, which one is your matrix and which one is your reinforcement? So you can look it up in the code. I guess it is somewhere in the 25th or 26th lecture, I suppose. So this is all for today as far as the concepts are concerned. So majorly we discussed about two things, which is the mechanical properties of the polymers and then the composite formulation, and typically the reason for why the composites are formed, And based on this composite formulation and what we have discussed right now, we will be solving a few problems within the next 5-10 minutes of our session. So if you have any doubts, you are welcome to ask me now, or otherwise we may proceed for solving the problems. Any doubts or any questions? If not, we you guys can go through this question. In case if anyone has doubts, please let me know. Meanwhile, who do not have any doubts on what we have discussed today related to the concept can go ahead with solving this problem. The question is very simple and direct. So let me read out the question. So it states that a unidirectional composite. So any idea on what is this unidirectional composite is? So it does not. It just means that these fibers or the reinforcements that you are going to use are typically in a are in the same direction. They are not having multiple orientation. They are all oriented in the same direction. So a unidirectional composite is prepared by using 70 percentage by volume of epoxy matrix and 30 percentage of carbon fiber. The elastic modulus is 3.5 gigapascal for the epoxy matrix, and for the carbon fiber it is 350 gigapascal. Calculate the longitudinal elastic moduli of the composite. So here what I want to say is that the elastic modulus of your reinforcement will be much greater compared to the elastic modulus of your matrix. The main reason is that because it is the reinforcement fiber that is actually going to carry out your load, is actually going to bear the load. So once you apply the load on the material, what happens is there is a stress transfer that happens. So the stress is initially it is experienced by your matrix, but as time progresses, the stress within the matrix decreases and the entire stress is transferred to the reinforcement fiber. So the reinforcement fiber is the one that actually bear the entire load that the composite is going to subject is going to be subjected. So So that is the reason the reinforcement have a larger elastic modulus compared to your matrix, because they are going to bear the load of the composite. I mean, of course, there will be contribution from the matrix, but majorly speaking, it is going to be the reinforcement fibers in case of load bearing applications. So now we are supposed to calculate the elastic modulus of the composite. So how to progress with this question? So can we write this in this way? Can I say elastic modulus of the composite is nothing but it is the elastic modulus, or you can say sum of the elastic modulus, let me put it this way, elastic modulus of component 1, or let me write it as E1, or let's say write it as EM, times EM is nothing but the elastic modulus of the matrix times volume of the matrix plus EF, that is elastic modulus of a filler or reinforcement, times volume fraction of the reinforcement. Can we write it this way? Let me center it. Is it okay, or is this fine? So then it's just now about plugging of numbers. It's going to be EM, which is 3.5 gigapascal, times, since matrix is the major constituent of the composite, so it is 0.7 here, and EF is 350 times zero point 0.3. So you just need to calculate the value. 353 that is 105. So elastic modulus of the composite is 107.45 gigapascal. Is this fine? Yes, I mean this should not be a very difficult problem because it's just one. So the elastic modulus of the composite is 107.45 gigapascal. So I hope there is not much doubt related to this question, and I hope it's a straightforward and a direct one. So let's move on to the next question. So it states that the tensile modulus of a thermosetting polyester resin and a glass fiber is 3 gigapascal, 80 gigapascal respectively. Again, here also if you see, the modulus of the reinforcement is greater compared to your matrix. If the tensile stress of 110 megapascal here is applied along the fiber direction on a continuous uniaxial aligned glass fiber reinforced thermosetting polyester composite with a fiber content of 60% by volume, calculate the resulting strain in the composite. So here you are given the tensile modulus of both the matrix and the filler. You are given what is the percentage of the filler or the fiber content in the composite. You are also told that the composite is going to be subjected to a tensile stress of 110 megapascal, which is along the direction of the fiber. Now using this, you are supposed to calculate the resulting strain in the composite. So this is also typically very similar to the previous problem. It's just that we have something uh, here we just have an additional step to calculate the strain based on the stress that is acting on the composite. So how to solve this? Anyone on how to solve this? So can we write this in the previous way itself? So first let us calculate the elastic modulus of the composite. So let me take this expression. Because we do not know what is the elastic modulus of the composite yet. We are just given the tensile modulus or the elastic modulus of your matrix and the fiber. So then the matrix is 3 gigapascal. So here the fiber content is going to be more, so it will be just 0.4 plus. Is this fine? 49.2 gigapascal. So after this, what we are supposed to do? We are just supposed to calculate strain, and we know the stress. So can we write it this way? So now we know the tensile stress, that is 110 megapascal. We know the elastic modulus of the composite. So we can calculate the strain, right? So just now about again, it's 49.2 gigapascal, that's equal to 110 megapascal by strain. So this strain will be nothing but 110 megapascal, that is nothing but 110 times 10 to the power 6 pascal divided by 49.2 times 10 to the power, sorry, pascal. So here we need to be careful with the units of conversion of megapascal and gigapascal. So megapascal is 10 1 so 1 megapascal is 1 in 1 1 into 10 to the power 6 pascal, and 1 gigapascal is 10 to the power 9 pascals. So then strain will be nothing but, so if we calculate this, then we get the answer as 2.235 times 10 to the power minus 3. Does strain have any units? No, right? So strain is a dimensionless quantity. So the strain is nothing but 2.235 into 10 to the power minus 3, and if you express that in terms of percentage, then what you will be getting is 0.2235 percentage. So this is the the resulting strain in the composite if the composite is subjected to 110 megapascals. So here there are two things which are key. So one is basically calculating the elastic modulus of how to calculate. Then the second thing is basically the units of conversion. So let me give that this side. So be careful with the units while solving these kind of problems. So I hope so. Is there any doubt related to this question? If there are any doubts, then please let me know, or else we can go to the next question. So moving on to the next question. I hope there are no doubts. Before going to this, let's solve the question 4. So that is quite here something that this question is a bit tricky. So tricky in the sense you should be aware of the terminologies that we are being asked to calculate. So anyway, let's look at this question once. Here it is mentioned that you are going to have a vulcanized rubber. I hope everybody knows what is a vulcanized rubber and why is the rubber vulcanized. So these two are things which you need to be aware of. So anyway, moving forward with the question. So a piece of vulcanized rubber of sample dimension 30 mm cross 30 mm cross 5 mm cross 5 mm, that is your length, breadth and height, is being subjected to a tensile force of 160 Newton. It is stated that the sample what you are going to have is going to be elongated, and this elongation is whatever the length of the sample you get after elongation is 200 percentage of your original length. So it means that your stretch ratio is going to be 2 under the same applied force. Calculate the true stress generated in the rubber. So how we will go about solving this question? And I also want to ask, how many of you are aware of the concept or of the terminology true stress? There is something, there is a difference between the stress that we saw right now. So those are called as the engineering stress or nominal stress. Here we are being asked to calculate the true stress that is generated in the rubber or vulcanized rubber in this question. So how are we supposed to calculate, or if anyone can tell me what is the difference between true rubber, extremely sorry, between true stress and engineering stress or normal stress. You can call them either engineering stress or nominal stress. Anyone, any whether the idea of what is the difference between true stress or and engineering stress? So the basic difference is, let me write it down. So engineering stress is nothing but, or nominal stress is nothing but, it is the force applied per unit area, but then the original area of the sample. So it is basically the area of the sample before it was subjected to tensile force, or before it was subjected to loading conditions. Now true stress is, it is almost the same except for the fact that the area what you are going to take under consideration for calculating the true stress is not going to be the original area of the sample, but it is the area of the sample after the deformation. So it's basically, you can say, the instantaneous area of the sample subjected to deformation of 160 Newton load. So it, the only difference that the only difference that is the only difference between true stress and engineering stress is nothing but the area that you take under consideration. Again, as I said, engineering stress is nothing but, here you take the original area of the sample even before the deformation is applied. That particular stress is called engineering stress, whereas in case of true stress, it is nothing but the area that we are taking under consideration in case of the true stress is nothing but it is the area of the sample after deformation. So both of them differ only in the aspect of the area that you are taking under consideration for the stress calculation. So typically why this happens is because what happens is, at tensile loading you're going to stretch your material. So the area of the material, so when you stretch, what happens is, mm, the length is going to increase, the material is going to elongate, but we know that the volume remains conserved in the system, right? So the volume is going to remain conserved, but the length is going to increase. So for volume to remain conserved, if the length is going to be increased, then the area need to be decreased. So that is the reason why the area of the sample after deformation is less compared to that of the original area of the sample that we are given with. So based on this, we can also do another claim that true stress will always be greater compared to the nominal or the engineering stress. Because the area of the sample after the deformation will be less compared to the area, compared to the original area of the sample, and hence true stress will be greater compared to your engineering stress. So let's calculate this calculate for this problem both true stress as well as the engineering stress. So let's calculate first the engineering stress. So force applied is 160 Newton. The original area of the sample, so here we are only going to take the cross sectional area, that is 5 mm cross 5 mm, or if you want to express it in meters, then so this is in case of engineering stress. So let's calculate the value at the end. So let it keep it as such. Now for true stress we need to do the conservation of volume, because the area is going to change. Volume. So then in that case what it is going to be is that your area times the length, let me put it as AO, original, oh, sorry, and then the length original equals to area after the deformation times the length after deformation. So it's going to be AO, or the original area, times the original length, area after deformation times the length after deformation is 200 times of its original length, so that is going to be 2L naught. So then AD will be nothing but AO by 2. So AO is nothing but the original area of the sample, that is 5 times 5 or 25 millimeter square by 2, which is nothing but 12.5 millimeter square. Oh, sorry. Now we know this, then it is simply again the same formula. So true stress will be nothing but it will be 160 by 12.5 times 10 to the power minus 6. Or if you want to keep it, you can either keep it in meter square or millimeter square, that is your wish. It depends upon the unit that you are asked for. So I am going to keep it in SI units. And your engineering stress is going to be 160 by 12.5, 12.8. So if you see here, true stress is nothing but it is 2 times that of your engineering stress. So this is how you calculate the true stress that is generated in the rubber and the engineering stress that is so true stress and the engineering stress in the rubber material. So is there any doubt related to this? Anyone? If not, or in case if you have, please you're welcome to let me know. So if you do not have any doubts, then let's move on to another question. So we are solving a variety of problems so that we can have a good practice over how to solve different questions related to the mechanical properties of the polymer material. So in that case, we have another one question where, so the question reads somewhat like this. So glass fibers in nylon provides reinforcement. The modulus of elasticity for each component of the composite is, for glass it is 10.5 times 10 power to the power 10, sorry, 10.5 times 10 power 6, and for nylon it is zero point 0.4 times 10 to the power 6. If the nylon contains 30 percentage volume e-glass, then calculate the fraction of the applied force carried by the glass fiber. So how do we solve about this question? Anyone? And also you have to take this into consideration that the glass fiber and the nylon are subjected to equal strain. And here we are asked to calculate the force, not the modulus or strain. The force, this, and not the stress also. It is the force. So let me just first write the parameters down so that. And E nylon, V nylon is, what would be V nylon? Volume fraction of the nylon. V of the glass, volume fraction of the glass is 0.3 as it is written in the question. So can I write this as, is this fine? Volume fraction of the glass of the nylon is 0.7. So we know these things, or we have these things with us. Now based on this we are supposed to calculate the fraction of the applied force that is carried by the glass fiber. So we are going to calculate the force or the applied force carried by the glass fiber to the total applied to the applied force on the composite. So how do we calculate force? And here it is said that the strain that is applied, oh sorry, strain that is applied on the glass fiber and the nylon are going to have, uh, or we can say are experiencing similar equal strain. So based on this we are supposed to calculate the applied force of the glass fiber and the applied force on the entire composite. Can we write it this way? Force applied as nothing but modulus times strain times area. So modulus is nothing but stress by strain. So stress is nothing but modulus into strain, and the stress is also nothing but force by area. So modulus times strain is equal to force by area. So force is nothing but modulus times strain times area. So we know this. Now can we use this to calculate the force applied on the fiber, glass fiber? So can I write this as E glass times strain? So that I'm going to keep it as epsilon, and this epsilon for both of them is same, so it will remain E, or it will remain as epsilon. So I'll change this as epsilon when I'm uploading the presentation to the weekly presentation folder. So there it will be changed, times the area of the glass. Similarly, force applied on the nylon will be nothing but E nylon times epsilon. Since the strain is equal here, in the I'm going to keep it as epsilon times A of the nylon, area of the nylon. Now the only thing that we don't know here in these two equations is the area of the glass and area of the nylon. But so can we express this area of the glass in terms of some other parameter? Can we write A or area of the glass as volume fraction V glass, volume fraction that the glass occupies in the composite, times the total area of the composite? Can we write this? So similarly, if that is possible, can I write this also? But let me know whether can we write this or can we write it this way. Sorry, A total, this is total in the sense for the entire composite, that area, that the cross sectional area of the entire composite. Can we write it this way? And here V glass and V nylon is not the volume, it is the volume fraction that the glass and the nylon occupies in the composite. Is there any confusion on how am I relating the area of the glass and the total area of the composite? So then if this equation is right, then can I re-express the force that is applied on glass fiber and nylon based on this equation? So let me number these equations. This equation, let it be 1, and let this be 2, let this be 3, and let the this one be 4. So if we write it this way, substitute or substituting 3 equation 3 and equation 4 in equation 1 and 2 respectively. Can so let me take another slide. So if I do that, then can I write force applied on the glass as E glass times epsilon times A glass will be now A total times volume fraction of the glass fiber. Can I write this way? Then similarly, can we write force applied on the nylon as modulus of the nylon times the strain times the total area of the composite times volume fraction of the nylon. Is this possible? Okay, we can write it this way. So we are just being asked to calculate the fraction of the applied force on glass. So can we write that as force applied on the glass divided by force applied on the glass plus force applied on the nylon. So based on this, if we write the equation, then it will be E glass, modulus of the glass times the strain times total area of the composite times volume fraction of the glass by similar, so this will be same in the denominator. Oh, so let me write it once again. Can we write it this way? So then is it possible to remove epsilon times a total area from the numerator and denominator because they are in common? So can we write this as modulus of glass times volume of the glass, so volume fraction of the glass by modulus of the glass times the volume fraction of the glass plus modulus of the nylon times volume fraction of the nylon in the composite. So that would be it. Now it's just about substitution of values. So 10.5, I'm going to take the 10 power 6 term common. So this will be nothing but this times 0.3 by 10.5 times zero point 0.3 plus zero point 4 times zero point 0.7. Is this fine? So now I'm going to take the 10 power 6 in the numerator and the denominator got cancelled with each other. So what will be this value? 10.5 times zero point 0.3, 3.15 by 3.15 plus 0.28. So that will be nothing but 3.15 plus 0.28, 3.43. So that will be, oh sorry, 3.15 0.918. So this is the fraction of the force that is applied on the glass fiber. So you can actually see here the major amount of the load is actually what is it is actually borne by the glass fiber. The nylon do basically, what you can say, it also does carry the load, but it's just only 9 percentage on the entire fiber. The 91 percentage of the load is actually carried by your glass fiber, that is the reinforcement that you use in the system. About it, I if you have any doubts, you are welcome to let me know. I think, oh, it's already 7:11, so we have already crossed our time. But anyway, we can, I think we can extend it to 5 more minutes. So if you have any doubts, please let me know. We do have actually three or four more questions. So few of these questions, I think you'll be able to solve this as a kind of an assignment or like a uh, homework. So or otherwise we will solve this in the next class. So if you have any doubts of what we have discussed till now, you're welcome to ask me right now. Any questions related to what we have solved, the four types of questions today? So all of these were the previous year gate questions, and there were also few more questions, but again those were the models of the same questions that we have discussed previously in the last 4 or 5 questions what we did today. So I hope we have almost covered on the entire mechanical properties of the polymers and how to calculate different parameters. If you have any doubts, then you're welcome to ask me. Please feel free to ask me, right, before we conclude our session for today. So if you have no doubts, then shall we conclude the session for today? So thank you all for joining today's live interaction session. The next live interaction session will be on 31st August, same from 5 p.m. to 7 p.m. I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to discuss with to interact with you all on this Sunday evening. So until we meet for our next live interaction session, have a great weekend and bye.